How's life in Raleigh?
Oh, more of the same. It's pretty good though.
That's good. That's good.
It's getting warm here at least.
No, is it? Oh, that's nice.
Yeah.
Here in Minnesota, it's around freezing. At
Around freezing, you said?
least, yeah, at least it was yesterday. I haven't actually been outside today. I'm
Mm.
stuck at home with a sick kid, so.
Oh, okay. Yeah.
Oh, Mendel, I know that you have probably lots of experience with Zoom seminars, but as with most such seminars, we usually wait a couple of minutes after the official start time because people
Yeah,
often join like right at the last minute, and that makes it easier.
of course. Yeah. Yeah.
We have a snow day in New Jersey.
Oh yeah? How much snow do you have?
Um, one
Snowed
inch
all
of
morning, but
wet
it's
snow or something on that order.
I
It
see, I
has
see.
thrown everyone into panic. Everything is closed.
I see, I
it's
see.
only like 2 inches or something. Yeah, it's not
Yeah,
bad.
but it's wet. It's like heavy snow.
Yeah. Well, yeah, I mean, even a couple of inches of snow in places where that's not super common really is a problem.
It used to be more common here, but now it's
Well, yeah, no,
it is slippery though. It gets very slippery. So
that's right.
mhm.
One of the worst places for snow that I've been in is Seattle because of how hilly it is and how
Mhm.
unusual it is to actually have proper snow in the winter. It gets to be an ice skating rink with very
Mhm.
high risk because of all the hills. Yeah. It's 11 Eastern, but let's wait a minute and see who else connects. Okay. Okay. Well, maybe it makes sense to get started and people will join when they join. Um, Today we're very lucky to have Mendel Nguyen join us from NCSU, and he'll tell us about some recent exciting work on ZN1 from symmetry, center vortices, effective field theory, things like that. So Mendel, please take it away.
Well, thanks so much. So my talk is going to be about based on this paper. written with Tinselmann Passage and Mithat Unsol. So I had magnetic monopoles and center vortices in the title. And these are, of course, two quite popular pictures of confinement, mechanisms of confinement. And I want to start by saying just a little bit about magnetic monopoles, which are undoubtedly familiar. At least going back to the 70s and 80s, this was, I think, the predominant picture of the confinement mechanism. The idea being that, much like in an ordinary superconductor, where the condensation of electric charges causes the expulsion of magnetic fields, if magnetic charges condense, then you get a dual version of that story. You get a dual Meissner effect, and this expels electric field, or causes, rather, their confinement. This picture is supported at least by the idea that in the Higgs regime, the semi-classical Higgs regime of SU gauge theory, there are magnetic monopole solutions, semi-classical solutions. And in the Higgs regime, they're heavy. But when you make these, as you go away from the Higgs regime, you can imagine that these magnetic monopoles are becoming light and eventually condense. So this picture has actually been realized in a handful of, analytically realized in a handful of models, the most well-known being the Seiberg-Witten model. But also it's there in the Polyakov model and compact QED, essentially, as well as some gauge theories in R3 cross S1. There's another competing picture of the confinement mechanism, however, which goes by the name of the center vortex mechanism. And briefly, what a center vortex is, it's a codimension 2 object, dynamical object. And the idea is that it's supposed to give a ZN phase when it links with a Wilson loop. So here I have a picture where this 1+1 dimensional picture. The vortex is just a point-like object. And the idea is that when it's inside the Wilson loop and then you compare it when it's outside, the difference in these two pictures is a ZN phase. And the idea is that the vacuum is filled with these center vortices. They are proliferating. And this proliferation of vortices gives rise to this severe destructive interference when you're computing a Wilson loop. And this destructive interference is what gives rise to an area law. I think it's fair to say that most support for this idea has come from numerical studies. And there's a very large literature on this. So perhaps another way to understand what center vortices are is to make an analogy with domain walls. So the slogan is that center vortices are for center symmetry, what domain walls are for discrete zero form symmetry. So let me elaborate on that. If I'm in the broken phase of a discrete zero form symmetry, then I have domain walls. I can, for instance, ensure a domain wall is present in the system if I insert a symmetry defect. Now, if my order parameter is a point-like object, and I can drag it through the domain wall, and the order parameter undergoes a symmetry transformation. And moreover, as I approach symmetry restoration, I'll see that domain walls begin to proliferate. So in other words, you can think of the mechanism of restoring symmetry as the mechanism by which domain walls are proliferating. So I think the idea behind the center vortex mechanism is completely analogous. Here you imagine that you're in a phase where the center symmetry is spontaneously broken. And this implies that you have heavy vortex-like objects, and these are the center vortices. And similarly, likewise here, the order parameter is some line-like object. And as you drag it through center vortex, your line-like order parameter is going to undergo a center transformation. So at least naively, you might expect that the restoration of center symmetry, confinement, is driven by the proliferation of the center vortices, just as an analogy, really, with restoration of discrete zero-form symmetry. Okay. But like I said, so the center vortex scenario. Sorry, is there a comment? Question?
Yeah, just wanted to ask, I know there is tons of literature on this, so
Yeah.
do people see a clear sign of this proliferation of center vortices numerically?
In some sense, yes, but I think what's kind of challenging about these studies is that it's kind of difficult, I think, to unambiguously define what is a center vortex. I think that's why it's been difficult to interpret these numerical studies.
Okay.
In other words, so I'll get into this a little bit later, but I think center vortices are well defined when you're deep in the broken phase. I think they're hard to make sense of when you're in the confined phase. Okay, so of course, Z symmetry is important in questions about confinement. I think it's agreed that to have a well-defined notion of confinement, you need to have a ZN one-form symmetry. It allows you to say that confinement is the phase where the symmetry is unbroken. So this leads to a question, somewhat separate question than what are the mechanisms of confinement? The question is, what are the generic phases of systems whose only microscopic symmetry is the one-form symmetry? I would like to consider this question, which seems different than talking about mechanisms. But as we go on, we'll see that our analysis of this question will have something to say about center vortices and magnetic monopoles. So the idea is that I would like to propose a framework for starting this question to determine the generic phases of systems with only a ZN one-form symmetry by beginning with the BF theory. So the BF theory describes gapped phases of broken ZN one-form. Basically, I want to assume my starting point is the assumption that my system can be taken to a regime where the ZN one-form symmetry is spontaneously broken. For instance, if I'm considering SUN gauge theory, pure SUN gauge theory, I can introduce Higgs, adjoint Higgs, that will break the symmetry group down to the gauge group down to Zn. So I assume this can always be done by an appropriate deformation of the theory. And I assume that once I enter this regime, the correct low energy effective description is given by this BF theory. The Lagrangian is here. It's this B wedge dA. I'm always going to use A for a 1 form and B for a D-2 form. And this theory has two symmetries. It has a 1-form symmetry associated with shifts of A, and has a D-2 form symmetry associated with shifts of B. And this is a very simple theory. It's topological. And basically, the full content of the theory is encoded in this basic correlation function. I take the Wilson loop of A with this Wilson surface of B, and the correlation function is a Zn phase if V and C link, V being the D-2 surface on which I integrate B, C being the loop on which I integrate A.
Can I ask a question about this?
Yes.
Is there a reason that you're taking the symmetry transformations to be exact? Like,
oh, this is, yeah, maybe I shouldn't have written it like this, but I just meant that locally, yeah, it's just, yeah, it's just a notation. I just wanted to,
that's fine. Okay, so
yeah,
so
I just
you
wanted
allow
to indicate that it's flat, but yeah, but not globally exact, but yeah.
That's fine. Thank you.
Okay. Yeah. Okay. Slides are a little bit out of order. Okay. Now, as in the previous slide, we had two symmetries, Zn1 form and Zn D-2 form. However, this D-2 form symmetry is not assumed microscopically. It's emergent. I want to deform the BF theory. Basically, I want to develop an effective field theory in which I only have the symmetry which is present microscopically. So I want to deform the BF theory. By deforming, just to be clear, by deforming, what I mean is that I'm allowed to make relevant perturbations, and I'm allowed to couple to heavy degrees of freedom. But then once I've introduced heavy degrees of freedom, I'm also allowed to make further relevant perturbations or tune parameters. Okay. Okay, so like I said, there's a D-2 form symmetry, which is not assumed microscopically. So we want to break it by coupling it to something else. We can break it by introducing objects which have gauge charge coupled to B. Now, these objects are necessarily of codimension 2, and they introduce into the path integral this factor e to the I integral of B. But as we've seen in the BF theory, this is just something which gives a phase to Wilson loops. Therefore, it's just completely natural to interpret as these objects that we're introducing as center vortices, because that's the defining property of them. However, okay, so having done this, we have broken the D-2 form Zn symmetry. But this actually introduces an unwanted U1 D-3 form symmetry. To understand that, note that before introducing center vortices, monopoles are not gauge invariant. So suppose we have a monopole configuration where the monopole world line or world volume is M. Then if I just insert this into the BF action and then consider a gauge transformation on B, I'll see that the BF action is not gauge invariant. Is there a question? Okay. So see that the BF action is not gauge invariant. And as you see here, in fact, it's as if it carries gauge charge N under the gauge group of B. What this means is that we can introduce monopoles in a gauge invariant fashion if we attach them to the junctions of N vortices. So at the bottom here, I have a picture illustrating this, say for N equals 3 and in 3 space-time dimensions. The blue dot is like the monopole, and these lines coming out of it are the vortices. Okay. So that's it. That's all we have to do. We introduce vortices to break a d-2 form symmetry, Zn, from the BF theory. We get an additional U1 symmetry at the cost of introducing an unwanted U1 symmetry. And then we break that by introducing monopoles. Now we have a system which has only the microscopic symmetry that we assumed initially, Zn1 form. And now we can consider what happens. What are the generic phases implied by this deformed BF theory, I'm calling it. Any questions about that? Okay.
So just to be clear, here we still have this UN symmetry that you mentioned, right? I mean, you haven't broken it yet.
No, I'm
broken
saying
by this coupling.
No, I want to say that I'm actually breaking it explicitly by introducing monopoles.
Okay.
Yeah. So we couple to vortices and to monopoles.
Okay. Both of them are dynamical. I mean, so
both of them are dynamical.
Okay.
Indeed.
Mendel, will you have a slide where you write the new effective action with?
Yeah, I will. Yes, I will. This is just at the general level, where it's just kind of wordy.
Okay.
Yeah. Okay, so roughly what we're going to do is we're going to try to understand what are the generic phases that we can get from such an effective description. And we're going to see that it divides into three possibilities. In the first case, we have neither vortices nor monopoles proliferating. In the second, both vortices and monopoles proliferate. And in the last case, vortices proliferate and monopoles do not. Notice that there's no phase, or there's no possibility where vortices do not proliferate, but monopoles do. And that's because of the comment about monopoles being attached to vortices. So if vortices are heavy and they don't proliferate, then monopoles cannot proliferate because they're always attached to vortices. Okay, so that was sort of abstract. I want to now go through this idea concretely in d = 2, 3, and 4 dimensions. So let's start in 2 dimensions. Here we have a symmetry which is Zn1 form and Zn0 form. The vortices are instantons and monopoles don't exist in 2 dimensions. So we want to break this Zn0 form symmetry. It's not there microscopically. And we can do that simply by adding these operators e to the ib. And this is a relevant perturbation because indeed it's actually the generator of the Zn1 form symmetry. And therefore is topological. And its scaling dimension vanishes. This was noted by a paper in a paper by Sherman, Jacobson, and Nusel. So we can always add such operators to the action. And if we do that, then we see that the physics described is a confining system. Basically because the BF model just describes these degenerate ground states. Adding this perturbation lifts this degeneracy. So in other words, what we learn is that the assumption that we can go to a regime of spontaneously broken Zn1 form symmetry is not robust because it can always be destroyed by a relevant perturbation. Confinement, therefore, is generic in 2 dimensions, which is a perhaps well-known thing, but this is one nice way of understanding it. Okay.
So just to clarify this, so in all the examples where we don't have confinement, there's always some extra symmetry that rules out these operators. That's the claim.
Exactly. Yes. Okay. Now let's go to 3 dimensions. And symmetry is now a Zn1 form times Zn1 form. Vortices are particles. Monopoles are instantons. Now to break Zn1 form associated with shifts of B, by the way, which I'm always indicating with a hat over the Zn, introduce a complex scalar phi, which has unit gauge charge coupling to B. So now we have dynamical charges. Doing so gives us an unwanted U1 zero form symmetry. And we break it by introducing monopoles, monopole operators. This results in the following effective action. And let me note that the monopole operator we see here is coupled to phi to the n. This again is the fact that the monopole itself, monopoles of A carries gauge charge, unit gauge charge under B. And so we have to dress it with these phi particles and n of them to get a gauge invariant operator. Also omitted is a possible potential term for B, but these are the essential terms. So let's see what can happen in this effective model. Basically 2 cases. If phi is heavy, then I can basically integrate it out. I can just delete phi from this effective action. And I'm left basically back with the BF theory that we started with. And this is the Higgs phase, deconfined. On the other hand, I could also have phi condensing. If phi condenses, then B gets a mass, becomes heavy. I integrate B out. And what I'm left with is a U1 gauge theory involving only A. It has a Maxwell term, and it's perturbed by monopole operators. This is basically Polyakhov's compact QED, and this famously confines. So in 3 dimensions, the generic phases are a deconfined Higgs phase and a confined phase. Okay.
Mendel, can I ask a possibly stupid question on the previous slide?
Yeah, please.
So from the point of view of the microscopic theory, I understand why monopoles of A have to carry electric charge N.
Yeah.
But once you integrate out B,
yeah,
the field little b,
yeah,
it's somehow less obvious that that has to continue to be true. I mean, at the level of just effective field theory,
yeah.
is it just misleading to think in terms of an effective action just involving A and thinking that the monopole?
Maybe there's a
is just-
subtlety, but I'm just, I mean, if the gauge group of B is Higgs, then I think I can basically forget about it. And
Uh-huh.
I think that's basically what I'm
Oh,
saying.
I see your point. So
Yeah.
good. When phi is condensed, the fact that this monopole operator term has phi's in it just doesn't matter. It's just essentially it's just a rescaling of the coefficient in front.
Exactly.
That's your point.
Right. Exactly.
And that's why it's okay. I'm sorry. I slow on the uptake this morning. Okay. Thank you.
Yes, indeed. I have this VEV. Yeah. Okay.
And
Right.
one more question. So from this point of view, why can't you imagine that this monopole operator would condense rather than phi, and that would have some other implications?
Well, it can't be the case that the monopole operator, the monopoles proliferate, but phi is, say, heavy. Because if phi is heavy, then I lose the monopole term in the effective action in the top. So in this case, there is no phase. Well, this is part of the general claim that we cannot have a situation where monopoles proliferate, but the vortices are heavy. Just because monopoles are always attached to these vortices. Okay. Okay. Now we come to the most interesting case. It's 4 dimensions. And I'm going to be schematic here because shortly I'll go to a lattice model to make this all precise. In 4 dimensions, the symmetry is Zn1 form and Zn2 form. Vortices are strings, monopoles are particles. As usual, we're introducing vortices to break this Zn symmetry associated with shifts of B. These are strings with gauge charge 1. Gain the unwanted U1 symmetry, and we break it by introducing monopoles. And in this situation, we actually have all 3 possibilities. Vortices can be heavy. And if they are, then they screen B. I'm sorry, vortices are heavy. Then if they are, then basically we get back to the BF theory that we started with, and this is the Higgs phase. But if vortices proliferate and monopoles proliferate, well, this is a confined phase. And finally, if vortices proliferate and monopoles do not, what we'll see is that this is actually a Coulomb phase. This actually produces a massless photon. One way to understand that, we'll go into this in more detail when we talk about a lattice model. But one way to understand it is that if monopoles are heavy, then you do have this U1 one-form symmetry emerging. But this will have a mixed anomaly with the Zn symmetry, one-form symmetry that we're assuming microscopically. And it's basically an anomaly between an electric and a magnetic one-form symmetry. And so it's natural that this is leading to a Coulomb phase.
So just before you go to the lattice, so in this language, how do you think about phases where the theory is just infrared free? I mean, so.
Well, this is the case C. This is the case C.
Okay, see, I thought you said it was an abelian phase, but infrared free, you'd have non-abelian
abelian
gluons and so on at low energies, so it seems somewhat different. But so do you think of that as some limit of the Higgs phase, or where does that fit in?
If I have free gluons, can I not think of them as
I mean, possibly you have
let me try to.
You have lots of extra symmetries there, of course, in infrared, so they
Yeah.
I guess. But
Yeah, let me see if I can come back to it if I think of something good to say.
Thanks.
Yeah, thanks. Okay, so I'd like to make this more precise in the context of a lattice model, where you can see this all very concretely. And in particular, I want to talk about Zn lattice gauge theory. Okay, so the action is in the Wilson formulation is given by this. I have a Zn valued link variable A, and the question is, can this Zn gauge theory on the lattice have a photon phase? For generic N, that's not so obvious. I mean, it certainly has a confined phase at strong coupling. It has a deconfined phase at weak coupling. But it's actually the case that for sufficiently large n greater than 5, greater than or equal to 5, I think, that an intermediate Coulomb phase has been observed. And maybe that's not so surprising for large n, because for large n, Zn starts looking a lot like U1. But anyway, we'd like to understand whether Zn gauge theory, lattice gauge theory can have this Coulomb phase for any value of n. How can we achieve it with an appropriate deformation? So in the lattice formulation, the definition of center vortices is quite precise. So what you do is you take the world volume of the vortex, think of it as a closed surface in the dual lattice. Here in my picture, I have a black line, which is supposed to be the world surface of the center vortex. I guess this picture is d equals 3, but try to imagine in d equals 4. And every place that this surface in the dual lattice intersects a plaquette in the original lattice, these plaquettes have dA, the flux is 2 pi over n. And everywhere else, the flux is 0. So this is the definition of a center vortex in the lattice model. It's this particular kind of configuration. Now, it's convenient to pass to an alternative formulation of the lattice model, which is the Vallon formulation. And this basically amounts to replacing the action with a quadratic action. It was initially motivated by considering the large beta limit of the Wilson action, but here we're just going to take it for any beta. We expect them to have the same universality anyway. And so in the Vallon formulation, in addition to the link variables, which are 2 pi over n integers, we also have to introduce a plaquette integer, m, and this is to ensure the periodicity, or in other words, the compactness of the gauge field. So in this formulation, in contrast to the Wilson one, monopoles are manifest. So I can think of a monopole current as just basically d of m on a cube. So this, if I take the sum over all these plaquette m's over the faces of a cube, this gives me the magnetic charge in that cube. So now we want to understand what are the effects of vortices and monopoles in Zn lattice gauge theory. And the cleanest way to do that, at least initially, is to just completely isolate the effect of vortices from monopoles. We can do that by just eliminating monopoles altogether. This means that we require that dm is vanishing. And a nice way of doing that is to use this trick, this modified Vallon trick, which has been used a lot recently, is to just introduce a Lagrange multiplier, denoted here a twiddle, and this is a real valued field. And integrating out just enforces the constraint that dm vanishes. So this is a model in which there are vortices. I can talk about vortices, but there are just no monopoles. And in particular, if I crank up beta, I can ensure that vortices are proliferating without worrying about what monopoles do, because monopoles are gone. Okay, but having introduced this Lagrange multiplier, we of course gain an additional U1 symmetry, which acts as shifts of A, continuous shifts of A, twiddle. And we're going to keep it for now. Okay. So let's now ask what happens when vortices proliferate, when beta becomes very large.
Mendel?
Yes.
Can I ask a question? I'm sorry, I'm a little bit delayed to ask this. So why are you not taking A to be real? Why are you taking A to be an integer multiple of a particular factor? A2 pi over n.
Oh, you mean here?
Yes.
Here. Well, this is because, yeah, so this is not, I'm considering Zn lattice gauge theory.
Okay, somehow I assume that that is achieved by, all right, never mind. I think I understand you.
Okay, thanks. Okay. All right. So we want to know what happens when vortices proliferate and beta goes to infinity. What is the phase of the system? And we can answer that immediately by performing an exact lattice duality, which is achieved very simply by Poisson resummation. So here we have an exactly dual action where we have traded the original Velan variable denoted M, the magnetic plaquette variables, with a dual magnetic plaquette variable, M tilde. And we see here that this is just nothing but a Velan formulation of U1 gauge theory, which is a partially modified Velan in a sense. The original gauge field A now turns into a Lagrange multiplier, basically restricts the dual monopole charge to be multiples of n. Now, we were interested in large beta. This is where vortices are supposed to proliferate, but large beta here in the dual formulation is weak coupling. So we have weak coupling in a U1 gauge theory. This is certainly in a Coulomb phase. There's no question about it. Now, we want to argue that this Coulomb phase persists when monopoles are not entirely eliminated, but just reintroduced with a very large mass. I think this is essentially clear, but we can be a little bit more precise about it. So what happens when we reintroduce monopoles? This explicitly breaks this U1 tilde symmetry under shifts of A tilde. But in the dual formulation, A tilde is the fundamental gauge field. And so this explicit breaking of shifts of A tilde, we can think of as coupling to electric matter, heavy electric matter in the dual formulation. So in other words, the dual formulation is a gauge theory, U1 gauge theory, coupled to charge n monopoles and very heavy electric matter. And then we're interested in the very weak coupling regime of this U1 gauge theory. Well, the only thing new in this case is that we have very heavy electric matter. And this certainly can't change the fact that we have a Coulomb phase. So that's our conclusion. This Coulomb phase is robust. It exists even if monopoles are there, but are just made very heavy. So here is my phase diagram for this Zn lattice gauge theory. Like I said, for n greater than or equal to 5, it's actually been observed that we don't actually have to do anything to the conventional Wilson action. We'll just find the Coulomb phase at an intermediate value intermediate values of the coupling beta. For n less than 5, we have to do something. We have to make monopoles heavy, but we'll eventually find this Coulomb phase.
Can I ask a question about this?
Yes.
Is there some first principles argument that one could give that for some reason the value of n actually matters? And there's, you see, in the picture that you show for n greater than equal to 5, it is not possible to go directly from the confined phase to the Higgs phase. You have to go through the Coulomb phase. Is there some deep reason for this? Or is it just for the moment observed numerically?
Yeah, I honestly don't think there's a deep reason for it. Maybe there is, but I certainly don't know it. Maybe Tin or Mitak would know, but
I mean, I have a vague recollection. There's a paper by Clay Cordova and somebody else, which argues that for some special values of beta, there are extra non-invertible symmetries that might force the theory to be in the Coulomb
yes,
phase or something. But
right.
I'm not sure if that applies in this particular setting. Well, maybe worth thinking about.
Yeah, that would be an interesting possibility, but
Okay.
yeah,
Thanks.
yeah. Okay.
So these graphs that you're showing, I mean, to what extent have they been numerically validated?
So n equals 5 is validated. N greater than or equal to 5 is validated.
Also true assuming mu, or you mean just for mu equals 0?
Oh, I'm sorry. Yes, for mu equals 0.
Yeah, but for mu, have you tried to also numerically test it?
So this I think would be very interesting to actually confirm. Yeah, numerically. I think it would be very, very interesting to find Coulomb phases for these low values of Zn gauge theory. I think the existence of a Coulomb phase for low values of Zn is actually quite surprising.
I think maybe I can make a brief comment. I think
yes,
pretty soon there will be publicly available. There'll be a publicly available Python package that will allow you to do Monte Carlo with this stuff pretty easily. It's in development.
Oh, okay.
Yeah.
Exciting. Okay. Yeah. Okay, and equally surprising, I think, is that in addition to the fact that you have a Coulomb phase for these low values of n, is the fact that it's associated with the proliferation of these vortices. Proliferation of vortices, rather than restoring the Zn symmetry, lead to a Coulomb phase. Okay. So finally, I'd just like to mention that we can also have additional phases where we actually have multiple photons. From the continuum point of view, this is, of course, kind of natural if I think about, for instance, taking SUN gauge theory and Higgsing it to an abelian subgroup. I can Higgs it in particular to its maximal abelian subgroup, UN to the n-1, and this gives me n-1 photons. This would perhaps be surprising in a Zn lattice gauge theory to have up to n-1 photons. Here I just indicate how you might see this. So I can start with, you can imagine taking the Wilson action, just adding a bunch of these other terms. Where here in the first equation, R goes from 1 to n-1. These are all legitimate things I can add. And this basically has the effect of just dialing the relative importance of all the various charged vortices. So, you know, I can distinguish the action. I can independently vary the relative importance of charge 1 or charge 2 or charge 3 and so on vortices by dialing these parameters beta R. Okay, and then as before, we want to pass to a Valon formulation. And then initially, just completely eliminate monopoles so as to isolate the effect of vortices. And we do the same thing. We introduce Valon, a modified Valon action. We introduce Lagrange multipliers A tilde. We now have n-1 of them, A tilde R. R goes from 1 to n-1 as before. And we have an exact lattice duality here, which gives us this dual action, which is basically n-1 U1 gauge theories. Okay, and then for very weak coupling of this U1 to the n-1 gauge theory, I certainly have n-1 photons. And then
a question.
Yes.
Sorry to interrupt. What is the one form symmetry here? Is it
well
to the n? Is it
no, it's Zn. It's Zn. Well, okay, it depends. So if I take the Wilson, well, if I take the Wilson thing, it's certainly just Zn, right? because I mean I haven't introduced new fields or anything like that.
I see. So A is still a kind of
yes, A is still a 2 pi over n link variable.
And basically what all you're doing is you're saying, yeah, actually this action that you're writing now, the top action on this page is actually the generic action you would write for a Wilson formulation Z engaged theory.
Indeed.
It basically using only the first term, which you implicitly did earlier.
Yes.
Is a too strong assumption.
Indeed.
All of these are allowed. Okay, that's the point. Okay.
Yeah, exactly.
And okay, good. I see. And now with this setting, you will actually get the generic possibility for a Coulomb phase, which is -1 photons. Okay, beautiful. Okay.
Precisely. Yeah. Right. Okay. So let me summarize. So we have we started with the question of asking what are the generic phases of a system which has only a ZN1 form symmetry. And we proposed that a nice way of understanding what the generic phases can be is to just start with the simplest, topological field theory, basically, this BF model. And then just using basically just the basic idea of effective field theory is just to ensure that all the symmetries are there, that there are no spurious extra symmetries. We talked about a fairly systematic way of achieving this. And kind of surprisingly, it involved the introduction of center vortices and magnetic monopoles. And this is a system which clearly has both, and we can actually ask what are the roles of each. I think one of the surprises here is that, contrary to the expectation, the proliferation of vortices is not enough to guarantee confinement. In other words, the proliferation of vortices is necessary, but not sufficient. Indeed, if they proliferate without the proliferation of monopoles, then rather than confinement, you get a Coulomb phase. Now, it's worth noting that in the numerical studies, people have often talked about what happens when you kill the vortices, you take them away. And indeed, it was observed that taking away vortices leads to the loss of confinement. That's completely consistent with what I just said, that they're necessary but not sufficient. But I think probably, in my opinion, there was not enough emphasis on the fact that they are not sufficient. So I think that's one of the major lessons of this work. But anyway, that's all I have to say. Thank you for listening, and I'd be happy to take any more questions.
Thank you, Mendel, for a very interesting talk. We had a bunch of questions during the talk, but are there more questions from the audience? It looks like Ofer has a question. Go ahead.
Yeah, so I'm a bit confused about whether this U1 to the n-1 theory that you're getting from the lattice is the same as the Cartan subgroup of SUN or not, because naively it seems like the monopole charges are not the ones that you would expect under the Cartan, which would be like the dual weights of SUN or something. So is it really the same U1 to the n-1 or is it a different one? I'm not sure.
That's a good question. I would have expected that they were.
Yeah, okay, but probably you can test that by just matching the monopole charges and things. So it's not obvious to you. Maybe it is. It's just not obvious.
Yeah, I would have expected that they are, just in terms of counting. But if there's, yeah. But yeah, indeed, that is the correspondence that I'm thinking of. I can break, in continuums, SUN can be broken to any, U1 to some P up to n-1, and this is precisely accounted for in this lattice model, that I can get up to n-1. Yeah.
you thought at all about this infrared free part of the phase diagram? I mean, I think when Ofer brought it up, he also mentioned that if you hit the infrared free regime, you also, I think, necessarily will get extra global symmetries for the ride.
That's true. That's true.
But it would be kind of interesting to try to track that, like try to think like, okay, so what if there are extra zero form symmetries that act on the matter fields? How does that,
right?
It's not obvious to me how that would be built in here, but it might be interesting to understand.
Well, also, they would be exact. I mean, there was a few immersion to low energies or something. Well, assuming you have some other UV starting point, which flows to this infrared free theory.
Right.
So it's not obvious.
But in the effective field,
how to fit them in.
Yeah.
But so in that case, the only way, right. So our starting point would have to be different then, right? So we'd have to assume microscopically extra symmetries.
That's right. You would have to
I don't think so.
assume.
Microscopically, you could just have some high energy asymptotically free theory, let's say Higgs to some infrared free theory or something. You don't necessarily need extra symmetries in the UV. I don't think, at least. But okay.
But that might be UV, I guess,
Progress.
from the point of view of this analysis. In some sense.
From the point of view of the effective field theory analysis, you probably do want to assume extra zero form symmetries.
Yeah.
In the UV, they might not be exact. Although I'm not even sure about that, because in practice, for example, to hit the infrared free regime of real QCD or that of adjoint QCD with fermions, you need the fermions to all be massless, and that necessarily gives you extra symmetries, as far as I understand.
Yeah.
Like, it's not obvious to me you can get away without it. But I think it's an interesting potentially open problem to build that in.
Yeah, I think it would be very interesting to build it in, but I think we'd have to assume, extra symmetries.
So, Mendel,
Yes.
In the examples you were giving, there was this relation between monopoles and these vortices, that you always had to attach vortices to these monopoles to make them gauge invariant, right? Is that
right?
Is that a generic thing, or is this something about this set of examples that you were? Sorry.
Yeah. So okay, I think that's a good point. So this observation is. I hope maybe I didn't mention this. So this observation is kind of old in a sense. It goes back to, lattice, lattice studies that monopoles always live at the junctions of vortices. This was an explanation from the continuum. I think that it is true. I think it's true when you're in a regime where where both are heavy, certainly, where this is you can reliably say this. Indeed, we're using this at least in this argument, we are really using this BF argument. In fact, in this lattice model, I don't think it's strictly the case that that monopoles are in the junctions of vortices.
Okay, thanks. I'll think about it.
Yeah.
Thank you.
Yeah.
I have one more question. So about the 2D version of all this. So,
which you understand better than I do.
Well, I don't know if I do. I have to say, to this day, I still have some confusions about it. So, for example, there's some regime in the parameter space of 2D adjoint QCD where it has both a Z2 chiral symmetry, which would act on your B field by a shift of pi, but also can have this not weird non-invertible symmetry. And it's not clear to me how it would act on on B actually. There's probably people who know this better than I do understand it, but I don't understand it. And in particular, you see, for generic N, the potential you would need to add to completely kill the confinement is more complicated. It has many terms, okay? But if you have a Zn chiral symmetry, you can forbid all of those terms. Yeah, give me a second, Mishenka, 1 second. So, but if you only have a Z2 chiral symmetry, I don't know how to forbid all the potential terms. But then you say, okay, I have this non-invertible symmetry.
Yeah.
It's not completely clear to me how to understand how it acts on the fields in the Zn effective field theory.
Yeah, I was wondering about that too, but I just don't know enough about it.
Okay. Well, fair. I'm also confused about it, and
yeah,
might be fun to understand someday.
Yeah, I think so too. Yeah.
Okay.
And also for the case of also for massless scalars, I mean, one could try to ask similar questions where you don't have chiral symmetries, and there probably you do need non-invertible symmetries, or well, I don't know. I don't think it's been analyzed enough, but
yeah.
Any other questions? Okay, if not, then thank you, Mendel, again for a wonderful talk. I learned a lot. And I'll send further announcements about future seminars. I think we're going to skip the one in 2 weeks by some requests to skip a week, and probably resume on March 12th. But I'll send an announcement with some details.
Thank you all.
Thanks everybody.
thank
See you
you.
soon. Bye-bye.
Bye.